So this is not a problem from the textbook, but it is very similar to the one we just did, which was this one. It was just finding out what is the magnetic field at different points due to this conductor, right? So here, on the other hand, we have two things going on. We have one wire like this, where the current is coming out of the page. Now we other have this kind of like wire shell, I suppose you can say, where the current here is going into the page. So this has current I2, and this has current, this is current I1, and this is current I2. I1 is 1.08 amps, I2 is 3.20 amps. We are then told that, okay, the distance between this point and this point is D, this point and this point is D, and this point and this point is D, where D is equal to 1 millimeter. The first question says, what is the magnetic field B at point A? So right here, what is the magnetic field? What we're going to do is draw out our Amperian loop. So our Amperian loop starts off at A and does a circle. Now Ampere's law says this. It says the path integral along this path here of B dot ds is equal to mu naught times I, where this is how much current do I have inside my Amperian loop. The only current I have here is I1. We also know here that whenever we have a situation of this simple geometry, this B and ds are in the same direction, so they're parallel. So it means that B dot ds is just B ds. And it also means that here, because we have a very simple geometry and everything's uniform, B is the same at every point here, which means we can pull B out and we get B, and then here we have, well, what is the circumference? It's 2 times pi times d, where d here, it's the radius of this Amperian circle. This is equal to mu naught times I1. Put everything onto the other side, so we just have B on the left. Plug in, this is mu naught. This is I1 divided by 2 times pi times d, the distance 1 millimeter, and we get this, 216 microtesla. Where is the magnetic field pointing? At this point here. Remember the second right-hand rule. So you're having your thumb pointing out of the page, and you're looking at where your knuckles are like turning or like rotating. So we know that they're doing like this clockwise motion. But essentially at this point here, exactly like on this radius here, the direction of the magnetic field is straight up. At this point here, the magnetic field is this way, right? At this point, it's like this. Here, it's straight down to the right, but here at point A, it is upwards. We then want to know, what is the magnetic field at point B? We use the same thing here, where instead we have B times, well, if we draw our Amperian loop, starting off at B, we obviously have a much bigger loop, and then we see, well, what is its radius? It's d plus d plus d, 3d, so we have that here, and that's going to be equal to mu naught times I. Well, remember, this is how much current we have inside, coming like through this loop, and we have I1 in the positive direction, I2 in the opposite, so negative direction, so we have I1 minus I2. From this point on, it's the exact same thing though, where we're just plugging in our numbers and solving for B. We see that here B is 1.41 microtesla. Where is it pointing? Well, here, what we actually get is this negative sign. So we know that it should either be pointing straight up or straight down, depending on like which one wins. By that I mean, is this negative current winning or is this positive current winning? And because we have this negative sign here, we know that it's going to be opposite as compared to here. So that means it's going to be pointing downwards. And that is it for this problem.